So let's just talk about circuits with capacitors. So these circuits are called RC circuits because there is like an R resistor and a C capacitor, and we would like to understand what happens in this circuit. Suppose you start with like a capacitor which is uncharged, and this, of course, everything else is neutral, and you close the switch here, and we would like to understand what happens, right? So we can immediately label the elements in circuit. So for example, this is the EMF, and it seems like the problem is not asking for any internal resistance, so I'll take it as it is. This is the resistor, and I know if there is like a current through the resistor, there will be a corresponding potential drop, which will be given by V is equal to, does anybody remember? What is the potential drop from a resistor? IR, right? Exactly, I times R. And for the capacitor, how do we calculate the potential drop for a capacitor? Or does anybody remember the definition of capacitance, C? So C, exactly, right? So C was equal to amount of charge you can put per applied voltage. From this, I can obtain the potential drop here, which will be equal to Q over C. Okay, so basically I have three sources. I have the battery, I have the resistor, I have the capacitance. So when I sum them up, they should be equal to 0. So let's do this. I have E, or I can write it like the potential provided by the battery should be equal to potential drops in the circuit and the resistor, right? In the capacitance and the resistor. For that, I'll write it as like I times R plus the other one is Q over C. Now, how do we solve this equation, right? What can we do about this equation? Suppose resistance, capacitance, and the EMF are given, and I want to find the current. How can I do this? So the current is written in terms of Q, but I don't know Q. Exactly, right? Current is given by dQ dt. So what this equation is saying, the current you got is equal to amount of charge accumulated in the capacitor. Obviously, if there's no charge accumulation in the capacitor, right, there cannot be any current because this thing is disconnected. So your current is as much as your charge on the capacitor. So let's put these things together and see what we can do about this. So E is equal to some R times dQ dt plus some 1 over C times Q. All right? How about this equation? Can we do anything about this? So general strategy, okay, these things are called differential equations. And since there's only the first derivative term, this is called the first order differential equation. And if you have never seen these equations, don't be scared. First order differential equations are very simple. All you need to do is to separate this dq things in the equation from the dt things. So how can I do this? I want to separate all the things with the q from all the things with the t, and I can have some overall constant. So let me try to do this. So the first thing I want to do is, okay, let's divide everything with R. So this is R, this is R, and now I can delete this R, okay. I'm trying to eliminate, I'm trying to put everything with Q on one side, everything with T on the other side. That's what I want to do. And now I want to take this equation and put it like this. dq dt is equal to E over R minus Q over RC. Now this side is purely written in terms of Q, like E, R, and C are constants, so I don't care about them. So what I can do is I can take this guy to this side and take this dt to this side. And let's see what happens. So I will just take this guy to here, take this guy to here, and something like that. Maybe I can write it a little longer. Okay. Now I can integrate both sides, right? Let's integrate from at t, okay, from time is equal to 0 to some final time t. And I want to assume, okay, let me put this guy a little bit to the side. So this is like that. I want to assume at t is equal to 0, I have 0 charge. And at t is equal to t, I have some charge q. And that's the charge I want to determine. Okay. Now I can take this, right? I mean, the right-hand side is basically t. And left-hand side, does anybody know the integral of left-hand side? How can we integrate this guy? You are integrating over q and you have like linear in q term. And remember that if you have 1 over x dx, this is ln x, right? If you have 1 over a plus x dx, you have ln x plus a. And if you have 1 over a plus b x dx, you should have something like ln ax plus b, and I have an overall a. To get rid of that, I need to divide everything with a. So this is, I mean, the only integral is ln. You can manipulate this integral in different ways to get what you have here. And here, for example, the a, the constant in front of x, is going to be this guy, right? So let's do this integral then. I think it says already done. This is ln e over r minus q over rc. And I want to put integral limits 0 to t. And we found that this guy is equal to t. Let's write this too. This is equal to t. Now, if I put the integral limits, I have something like this: ln e over r minus q over rc. And we said integral limits was actually like this, from 0 to q, so that we can find things in terms of q. And this is ln, if I put q is equal to 0, I have e over r. Now let's combine these two ln's. I don't want to write them separately. So this guy divided by this guy, and there's like an overall parenthesis. Okay. Now I can solve it, right? The definition goes like this. If you have ln x is equal to u, that means e to the u is equal to x. So I'm going to use this. I think when I integrate, I forgot to multiply, right? Something like this, right? This is RC. Or I can put this RC to here, like this. Okay, now I can take it. E over R minus Q over RC should be equal to, okay, this is like n overall RC, this is like minus. I think you can just take the integral and take the derivative and then see it is going to be minus. And this will be equal to x minus t over RC. Now Q is equal to, okay, something C 1 minus e to the minus t over RC. Good. First, I started with this. I put it in this form, and I integrated both sides. When I integrated both sides, I had on the left-hand side, this guy, this is basically Ln, and on the right side, I have minus T over RC. And here, I was just trying to just do this, right? Ln x is equal to U. This equation means x is equal to, or x u is equal to x. That's what it means. Okay, let's clean this nicely, u. And after that, I basically, that's exactly this. Maybe I can do it one more time. So this is like x minus T over RC was equal to E over R minus Q over RC divided by E over R. And from here, I take this E over R to this guy, and I took this Q like this, and this guy like this, and I put like minus sign, and I take the Q, and okay, now since it's on the other side, there's no minus sign, and it's equal to this, and this is like RC, I multiply everything with RC to leave Q alone, so it gave me something like EC, this is something like EC, and when I take the parentheses of EC and EC, I had something 1 minus E to the minus T over RC. Now, if Q is known, I can calculate V, because V is written in terms of Q here. So let's do this using this equation. So then V is going to be equal to basically Q over C, which is E1 minus, okay, let's write the same form, E to the minus T RC. And if Q is given, I can take the derivative from here and calculate the current. And the current is I is equal to, okay, it's going to be E over, okay, this is like in the derivative exercise for you, but it's simple, minus T over RC. So you can see this RC just shows up everywhere. So it has actually a special name. It's called time constant of T circuit. Time constant. And let's plot this to see how this thing behaves. So I want to first see, for example, Q. I want to see V, and I want to see current. So at T is equal to 0, I can put T is equal to 0. 1 minus 1 is 0, so it starts from 0, something like this. And as T goes to infinity, this term drops, and it goes to a constant value like this. So it's going to be something like that. So V has the same form, something like that. And I, initially, you can see if T is equal to 0, there's no current. And as the capacitor gets, okay, sorry, at T is equal to 0, there's like a current E over R. But as T goes to infinity, this term goes to 0. This means this whole thing goes to 0. So it's going to be something like this. Okay. And this value, for example, is what we can read from the, this is E, C. This one is E, and this one is E over R. So for that, let's just, until that, then we can just solve a problem and see how this thing works. So the capacitance in the circuit of figure, I just deleted the figure, but it's the same, is C is equal to 0.30 microfarad, and the resistance is 20 kilo ohm, and the battery EMF is 12 volt. A, determine the time constant. Okay, let's start. We know time constant tau is R times C. This is going to be equal to 20 times 10 to the 3 ohm times 3 times 10 to the minus 6 farad. And this thing is going to be equal to what? 0.6 times 10 to the minus 2 seconds. Okay. And B, maximum charge the capacitor could acquire. Okay, let's go back. What we found, the maximum charge the capacitor could acquire is this. This is the Q max, and it happens when T is equal to 0. So B Q max is equal to EMF times C, right? EMF times C, and this will be equal to 12 times C is equal to 0.30 times 10 to minus 6 farads. So this is going to be equal to 3.6 times 10 to minus 6 coulomb. And C, time it takes for the charge to reach 99% of its value. Okay. Q of T is equal to Q max, which we calculated, and it's going to be equal to 1 minus e to the minus t over tau. And this should be equal to 99% of its value. What this means is 0.99 times Q max. So we can drop these guys, and we can find E to the minus t over tau is equal to, 1 minus 99 is 0.01. Then I can calculate it like t over tau is equal to ln 0.1, means 10 to the minus 2. That means, this is minus, that means that's minus 2. Then t is going to be equal to 2 times tau, what we calculate tau here. So it's going to be equal to 1.2 times 10 to minus 2 seconds. Okay, this is A, B, C. D, the current when the charge is half its maximum value. Okay, A, B, C, D. When charge is half of its maximum value, that's what? Q max times 1 e to the minus t over tau. This should be equal to Q max over 2. Again, I cancel these. Then from here, I find 1 minus e to the minus t over tau is equal to 1/2. Let's see if we can use it for the current. For the current, what we calculated here was E over R times e to the minus t over RC. So it's E over R times e to the minus t over RC. But we know e to the minus t over RC, e to the minus t over RC is equal to 1 minus 1 over 2, which is 1 over 2. So it's E over R times 1 over 2. And this is going to be 12 volts divided by 2 times 20 times 10 to the 3 ohm, which is going to be equal to what? Okay, this is 3 times 10 to the minus 4 ampere. What is ln 10? That's correct. 10 to the minus 2. Minus 2 times ln 10. Do I have ln on my graph? This is minus 4.6. You're right. This is minus 4.6. Then this one is going to be times 2 is equal to minus 9.2. Good job. Thank you. This is 9.2, right? Yes, right. Thank you. Good job. Yes, you are absolutely right. I messed up here. Thank you. So this is D, E, maximum current. Okay, we can find the maximum current. Okay, this is A, B, C, D, E. Okay, E I max is obviously E over R, which is going to be equal to 12 volt divided by R is twice that amount, right? We just calculated that already. It's going to be 6 times 10 to minus 4 ampere. And maximum current and the charge when current is about 20% of its maximum value, okay? F, so I is equal to I max times e to the minus t over C. And if it's equal to 1/5 of I max, I can cancel these guys and I find e to the minus t over RC is equal to 1 over 5. Then Q is equal to Q max times 1 minus e to the minus t over RC. This is going to be Q max. 1 minus 1 over 5 is 4 over 5. So if I multiply it with this number, what do I get? 2.88, something like 2.9 times 10 to minus 6 coulomb. Okay, good. So I have a little bit modification to this circuit. So now I want to think about a different problem. Suppose I charge the capacitor first. Okay, this, I think the book, it has like a typo here. It looks like a battery, but it should be capacitor. Suppose I charge this with some initial Q, and then I connect it to a resistor, and I want to ask myself, what happens when I close this switch, right? Now there's no EMF. This is so-called RC circuit without EMF, and we can actually deal with this circuit the same way. And for this, I remind you, this C was defined by Q over V, and this R was defined by V was equal to I times R. Okay. So here, the idea is whatever the potential difference you have here, it should be equal to here, right? So the potential difference for the capacitor is equal to Q over C. This should be equal to the potential difference across the resistor, but the resistor potential difference is determined by the current passing through the resistor. So that's I times R. But for I here, okay, let's look what we did here. We said I is equal to, can I use this exact same equation here? Maybe I ask you. Paste. Can I use exactly the same equation? So the answer is almost, but there must be a minus sign. And the reason for this minus sign is that here the capacitor is losing the charge, so it's like a decreasing charge. Whereas here it was charging, so it was increasing charge. You know, when something is increasing, its derivative is positive, and something is decreasing, its derivative is negative. So you have to compensate this extra negative here. That's your definition. So let's write this. Then Q over C is equal to minus R dQ over dt, or I can say minus T over RC should be equal to dQ over Q. Now integrate both from, integrate this side from 0 to T, integrate this side from some initial Q0 to some final Q, and we know Q0 should be bigger than Q at any time, or maybe if it's T is equal to 0, it may be equal. So the left-hand side minus T over RC, the right-hand side is ln Q, Q0 to Q, this is going to be ln Q minus ln Q0, or this is going to be equal to ln Q over Q0. Then I can just solve this the same trick. Ln X is equal to U means e to the U is equal to X. I use exactly the same thing. So from here, Q over Q0 is equal to X minus T over C, or I can take this Q0 to here. Maybe I can just clean up this a little bit. And that's my equation. Okay. And the same idea, if Q is known, you can calculate V is basically Q over C. So it's like Q0 over C exponential minus T over RC. And the current is the derivative with the minus sign. So for this, I have Q0 over RC exp minus T over RC. And I can plot these guys again. The first one the second one, and the last one. So this is like Q, this is V, and this is I. In this case, you can see all of them are decreasing exponentially. Let's use another color like this, like this, like this. And here, this is Q0. Here it is Q0 over C. Here it is Q0 over RC. Okay. All right, so one more example. So this is example 12 from your book, a discharging RC circuit. In the RC circuit shown in figure this, the battery has fully charged the capacitor. So Q0 is equal to C times E. You first charge the capacitor fully, and then at T is equal to 0, the switch is thrown from position A to B, from here to here. So when you connect to here, the battery is completely out, so it doesn't matter what it is. And the battery EMF is 20 volt and the capacitance is 1.02 microfarad. The current I is observed to decrease to 50% of its initial value in 40 microseconds. And the question is, what is the value Q, the charge on the capacitor at T is equal to 0, and B, what is the value of R, and C, what is Q at T is equal to 60 microseconds. We said Q of T is equal to Q0 e to the minus T over RC. And we know Q0 is the maximum charge it can get when the battery is connected, and we found it as E times C. Right? If you want to think about this, when the capacitor reaches the maximum when it is connected to the battery, there will be no current because capacitor reached the maximum. It cannot absorb more, so there cannot be any more flow. Then that means the potential difference across the battery should be equal to potential difference across the capacitor. So you just change in this formula, C is equal to Q over V, change V with E when this is attained. Okay. So what is the value Q, the charge in the capacitor at T is equal to 0? So let's calculate this. This is like 20.0 volts times capacitance is 1.02 times 10 to the minus 6 farad. And this is going to be equal to 2.04 times 10 to minus 5 coulomb. So what's the value of Q and B? What's the value of R? So here's I need to look at the question and see what information is given. The current is observed to decrease, something like that. Okay. So I of T is its maximum value, let's call it 0 consistently, times e to the minus T over RC. And they say at T is equal to 40 microseconds, this is going to be equal to half of its value, I0. So cancel I0s. Then, so ln 1 over 2 should be equal to minus T is equal to 40 times 10 to the minus 6 divided by RC. We are trying to solve this equation for R, so R is equal to, okay, this guy is minus ln 2, so R is equal to 40 times 10 to the minus 6 divided by ln 2 times C. Okay, if you put the numbers, this is like 40 times 10 to the minus 6. I found something like 56 ohm. Anybody else? 56 ohm, maybe 57. Okay, thank you. And C, what is Q at T is equal to 60 microseconds? Okay, C C, Q is equal to Q max, and its value we found, okay, this thing is Q0, 2.04 times 10 to the minus 5 times e to the, okay. Can I find it in a simpler way? Probably not, but that's fine. Exp minus 60 times 10 to the minus 6 divided by R is 57, and C is equal to what? C 1.02 times 10 to the minus 6. Okay, 10 to the minus 6, cancel again. So let me calculate this. 0.72, it's like 7.2 times 10 to the minus 6 coulomb. Okay.